Hi there, this lesson's gravitational potential and escape velocity, part of the gravitation topic for A-level physics. So what is gravitational potential? The gravitational potential of a point within a gravitational field is equal to the work that must be done per kilogram of mass in bringing the mass from infinity to the point. So you might look at that and think, what? And rightly so, to be honest, it's quite a strange, abstract concept. It will make a lot more sense once we do an example, so bear with it. So probably write that down and then write these further notes down. So gravitational potential at infinity is 0, that's important. Every other point for gravitational potential is negative. Gravitational potential is measured in joules per kilogram. And it's a scalar quantity. So if you want to make some notes, just pause the video. And then we'll move on. So the equation. The equation for gravitational potential is simply V equals minus Gm over R. So G is the gravitational constant, which is at the bottom of the page. M is the mass of the object, so maybe the planet Earth or the Moon or another planet, such as Mars, Venus, etc. And R is the distance from the centre of that planet. Let's move on then. So work done. There's another equation that will come in handy. We'll use it in the first example. So if you want to write this one down, work done is equal to mass multiplied by change in potential. So work done is obviously measured in joules. Mass is in kilograms. The change in potential is joules per kilogram. So I'd write that one down as well, and then we'll utilise both of those in the first example. So let's move on when you're ready. Before that, let's look at this. So variation of potential about the Earth. So this might be a graph that you see in an exam. And in an exam, typically what it might ask you to do is to calculate the gravitational field strength at a point. So it might say, what is the gravitational field point at, say, this distance? So what you would do in your test is get that point, and then just do a gradient with a ruler. And then you would do the gradient, changing y of changing x. So if you see a graph like this, a potential against distance, the gradient, the change in potential over the change in distance, is actually the gravitational field strength, G, measured in meters per second squared or newtons per kilogram. So if you see a graph like that, and it asks for the gravitational field strength at any point, so it could be this point, could be that point, you draw a tangent with a pencil and ruler, take the gradient, and that will give you the gravitational field strength. Hope that's okay. So here's the example. So I'll take you through this one, and then there's another example for you to have a go at. Or if you've done this at school, you may wish to have a go at it just for practice. So calculate the gravitational potential at the Earth's surface. So the first one, gravitational potential equation. V is equal to, it should be minus Gm over R, but given an answer as a positive value is okay. So G is given to us, it's 6.67. 6.67 times 10 to the minus 11, multiplied by the mass of the object. So we're on the Earth, so the mass is 5.97 times 10 to the power 24, divided by the distance from the centre. So the distance from the centre of the Earth is the radius, which is 6.37 times 10 to the power 6. So that gives us a potential of 62.5 megajoules per kilogram. So that's the gravitational potential at the Earth's surface. So let's do number 2 now. So gravitational potential, Gm over R, Let's put our numbers in once again. So G is the same, 6.67 times 10 to the minus 11, multiplied by the mass, 5.97 times 10 to the 24, and then divided by R. So this time it would be the radius of the Earth, plus the height above the Earth, which is 6 times 10 to the 5, which gives us a potential of 57.1 megajoules per kilogram. So let's do number 3. Calculate the work done in moving a mass of 1 times 10 to the 4 kilograms from the surface to the height of 6 times 10 to the 5 meters. So what we need to do is use the equation work done is mass times change in potential. Subtract the potentials from each other that we've got. The 62.5 megajoules per kilogram and the 57.1 megajoules per kilogram, and then just multiply them by the 1 times 10 to the 4. So we've got 62. It will be 5116, the original number to 5 significant figures, megajoules per kilo. Subtract the 57.1304 to 5 significant figures. Gives us a change in potential of 5.3812 megajoules per kilogram. The reason I've used 5 significant figures is because in an intermediate calculation, the minimum amount of significant figures you should use is 5. More than likely, in your examination, you should just use the entire number that's in your calculator. So we do that change in potential and multiply it by the mass of 1 times 10 to the 4 kilos. And that gives us a work done of 5.4 times 10 to the 10 joules. I've rounded up because that's the end of the calculation. It's actually 5.3812 times 10 to the 10, but 5.4 is suffice. You know, the question's giving figures to 2 significant figures. So the last one, calculate the work done in taking the mass of 1 times 10 to the 4 kilograms to a point where the Earth's gravitational effect is negligible. So this is a common question. So we need to do work done is mass times change in potential. And the mass starts on the surface of the Earth. So the potential at the surface of the Earth was 62.5116 megajoules per kilogram. And the point where the gravitational effect of the Earth is negligible is infinity. And at infinity, the gravitational potential is 0 joules per kilogram. So the work done in taking the 1 times 10 to the 4 kilogram mass to a point where the Earth's gravitational effect is negligible is work done is mass times change in potential. So the mass is 1 times 10 to the 4. And the change in potential is 62.5116 megajoules per kilogram minus 0. So just multiply by 62.5116 times 10 to the 6. And that gives us an answer of 6.25 times 10 to the 11 joules, or 6.3 times 10 to the 11 joules. Hopefully that example went okay. So we use gravitational potentials to figure out the minimum change in energy going between different orbits. So that's what it's used for. And then obviously you just need to remember the definition from earlier and regurgitate that in an exam, so to speak, so you pick up your marks for your definitions. But it's important to remember. You know, it's an easy 2 marks. So here's a question for you to have a go at. So if you want to pause it, calculate the minimum work required to lift an astronaut of mass 120 kilos from the Earth's surface to the height of the International Space Station. So we want to do the work done is mass times change in potential, and we need to calculate the potential at the surface of the Earth and the potential at a height that's 300 kilometers above the surface of the Earth. So we calculated the potential at the surface of the Earth earlier. So that would be V equals gm over r. Use the mass of the Earth and the radius of the Earth, and that gave us a value of 62.5116 megajoules per kilogram. And what we need to do is to do it for the height of 300 kilometers above. So potential is gm over r. So put the numbers in. So it's 6.67 times 10 to the minus 11 multiplied by the mass of the Earth, which is 5.97 times 10 to the 24, divided by the radius. So we've got the 6.37 times 10 to the 6 plus the 300 kilometers, 300 times 10 to the 3. So let's calculate that. 59.7 megajoules per kilogram. Now we've got both the values, we can calculate the work done. So the work done is mass times change in potential. So the mass is 120 kilos multiplied by, we need to do 62.5116, subtract 59.7 times 10 to the 6. And that will give us 337 megajoules of energy. So let's move on. Gravitational equipotentials. So surfaces that join up, points of equal potential. There is no work done by gravitational force when a mass is moved along an equipotential surface. Equipotentials are always perpendicular to field lines. Some examples, equivalents would be contour lines on a map, sea level, floor of a room, benchtop surface. So essentially, as an example, say we were at this point here, and you moved across this line to this point. Now you could be asked this in a question, or you could, it could go all the way around back to where it started and say how much work has been done against the gravitational force or the field. And the answer is 0, because, work done is mass times change in potential. And there is no change in potential. It's on a line of equipotential or equal potential. So the change in potential is 0, so mass times 0, work done would be 0 joules. It's a typical 1 or 2 mark explanation or description, or it can come up on multiple choice if your exam board has multiple choice. Let's move on to the next bit. Escape velocity. So escape velocity is how fast you need to go in a straight line to escape the planet that you're on. So you'll be doing work against gravity. So as we know, work done is force times distance. I'll call it F dot R for distance. And the force that we're doing the work against is the gravitational force. So G m1 m2 over r squared. If you've done my previous videos or done this at school, you should know that equation. Times r. So if we cancel these, the work done against the gravitational field is G m1 m2 over r. So this is the potential energy. And what we can do is make that equal to the kinetic energy, because we're going to be travelling faster to get to the escape velocity. So make that equal to the kinetic energy, half mv squared. And we can call this v escape. Cancel the m's, and then just rearrange. So v escape would be 2g m over r, square rooted. Going very useful. If you do astrophysics, you'll also use this for the Schwarzschild radius of a black hole. So I'll write that down because we're going to use it. And let's look at the next example. So what we're going to do is use that to calculate the escape velocity of the Earth. It's very straightforward. So v escape is equal to the square root of 2g over r. So then we just need to put our numbers in. So square root of 2 times g, which is 6.67, times 10 to the minus 11, multiplied by the mass of the Earth is 5.97, times 10 to the power 24, divided by the distance r, so surface of the Earth, 6.37 times 10 to the 6. Don't forget to square root. So the escape velocity is 11.2 kilometers per second. So if you're leaving the planet, so the planet Earth, that is not the straight line speed that you go up. You know, rockets don't do that. They actually go up a little bit, then start to, you know, it's the horizontal velocity that's the escape speed. They go, you know, they don't go vertically upwards. They go vertically upwards to clear any buildings or anything. Then they'll change trajectory. There's a video on YouTube where Elon Musk explains this, you know, this basic orbital mechanics principle in a pretty good manner, to be honest. So let's move on to the next one. So last question: calculate the escape velocity on the moon. So if you want to pause and have a go, very straightforward. For fun, you can practice where the escape velocity equation comes from. So V escape is equal to the square root of 2gn over r. So it's 2 times g, which we've used several times, 6.67, times 10 to the minus 11, multiplied by the mass of the moon, 7.7 times 10 to the 22, divided by the radius, which is 1.7 times 10 to the 6, and then square root. And that gives an escape velocity on the moon of 2.46 kilometers per second. Hopefully you found that video okay. Thanks for watching, and I'll speak to you soon.